Hey, welcome, ladies and gentlemen. Welcome to the Big Bear Math Channel, and we've got a monster bear to try to tackle today. We're revving up for the AP Calculus exam, and we've gone to the College Board website, and we've pulled up from the list of released past questions. We're in the 2018 packet. We're looking at question number 2. It is calculator active. And I'm going to try to leave a link below that so you can find this question yourself. If you haven't tried this question and worked through it yet, I highly encourage you to do so. Try to spend at least 10 to 15 minutes trying this question on your own using your calculator and see what you come up with, and then come back and watch the video and see if we came up with the same answers, and maybe see if maybe we came up with the same answers, but we took different approaches, which is always nice to kind of compare and contrast which one's more efficient, a little quicker, easier perhaps. So diving right into this, what I like to do is I'm a huge fan of, if I get a function like this, I'm going to enter that into my calculator right away. I'm hitting y equals, boom, get it in there so we don't have to retype it a bunch more times. So we said researchers are on a boat. They're investigating plankton cells in a sea. We're going to try not to get bogged down by the fact that I have no idea what a plankton cell is. And there's going to be times here where this is very hard to visualize. And at a depth of h meters, the density of the plankton cells in millions of cells per cubic meter is modeled by this P of H function. So depending on, maybe the deeper you go, the more dense it gets, or the less deep you are, the more dense it is. But it looks like the density is going to vary one way or the other the deeper you go. And then that function is only active from 0 to 30. And then after that, once you get past a depth of 30 meters, we start to rely on this new f of h function to describe the density. But that f function is not given explicitly. And that's one of their new favorite tags they like to do, is describe a function, but not give you the whole gist of it. So jumping into part A, which I was kind of just, assuming was going to be a piece of cake, it was far or anything from a piece of cake, at least the second half of it, because I think what you're going to see, we're going to be fine on this first part, but then interpreting the meaning is going to be the really challenging part. And so we're going to work real hard on that. So one of the advantages or nice things about having that function already typed in is when we want to evaluate p prime of 25, and again, we're not going to try to derive this function by hand. I mean, we could if we wanted to. Product rule is going to treat us okay. But what I'm going to do is I'm going to hit the math menu. Scrolling down that list, we're looking for option number 8. It's going to ask you, what are you deriving with respect to? So your first input is going to be the x. And then instead of retyping that function again, which you could, I think we're going to hit, it's going to be alpha trace. Alpha trace, it's going to allow you to import your y1. And so assuming you've already got the function entered into y1, it's just going to import it right there. And then we're going to evaluate that at 25. Hit enter, and you're going to get, negative 1.179. I'm gonna forego the units for a second, and we're going to discuss and kind of talk about our setup for how do I interpret the meaning of this answer within the context of this question. And if nothing else, this may be the number one takeaway that you want to focus on here today. All right, let's see if we can get a text box going. Open this bear up a little bit. So basically, in a general sense, when you say p prime of 25, what I'm thinking is that I've got a function p that is changing at a rate of, we'll say, negative 1.179, whatever's per whatever, okay? But I'm missing, really what we'll say, besides the fact that I'm missing my negative sign, I'm missing what I would consider 3 really, really key elements, okay? The first element that I'm missing right here, let's see if we can highlight this bear, is, I said something about function p is changing. I've got to be way more specific than that. Again, we want to dive into the context of this question, and I'm not going to, work too hard at this. I'm just going to basically copy the way that they defined and described function p right there. I do like the word changing. I could have said decreasing, but the key is that now if I said decreasing right here, then I wouldn't have this little negative sign in there. So the word changing is a neutral word for me. That's really not saying increasing or decreasing. I'm going to let the sign of this number right here describe, basically tell the reader whether it's increasing or decreasing. A couple other things I don't have. I don't have my units that we'll talk about here in a second. And I'm also missing what I call the specificity of including the fact that this is at a depth of 25 meters. So I'm going to include that somewhere in my sentence as well. Okay, so let's talk about those units because I think that's going to be the hardest part. And I'll try to explain this. So when you think of function P, the independent variable is H, which is weird. We're used to it being an X or a T, but for some reason, the independent variable is an H. And that H is measured in what? Meters. Okay. So our derivative was taken with respect to H. Our derivative is with respect to H. P prime of 25 was us deriving P of H with respect to H. All right. And that H is measured in meters. So here, I'm going to put it all together. Or let me see if I can write this out for a second. So you had a function that was already, we'll say, millions of cells per cubic meter, right? Well, when you derive that with respect to H, you're basically doing this, multiplying it by 1 over meters. So your new units are going to be millions of cells per, meters to the fourth. Very hard to interpret or, digest. So anyway, before we beat a dead horse down too bad, I'm going to go ahead and show you what my sentence is going to look like. So first of all, I want to address my specificity. I just like to get that out of the way. So I'm saying at a depth of 25 meters, okay? Now I basically want to describe function P, and we're going to say the density of plankton cells is changing. Again, there's our neutral word, changing, at a rate of negative 1.179. We'll say millions of cells. Now, here's one way you could say it. You could say per cubic meter per meter. And in cubic meter per meter is basically at the end of the day equivalent to m to the fourth. So that puts the finishing touch on part A. Thank goodness. We're ready to move on. All right, here we go. Part B, consider a vertical column straight down through the water, and every horizontal cross section has a constant area of 3 square meters. Interesting. Okay. To the nearest million, how many plankton cells are in this column of water, starting from basically the surface of the water onwards down to 30 feet deep? So again, I don't know if I'm going to be able to draw the best picture here to try to describe what they're saying, but I'm going to give it a shot. So here's the surface of the water, and we're basically picturing a column that goes straight down for 30 feet. And they're saying every cross section, let's say a thin slice here, or a thin slice here, or a thin slice here, every one of these cross sections or slices has an area of 3 square meters. And at the end of the day, we want to know how many total in million to the nearest million plankton cells there are within this 30-foot column. And sometimes when I get myself into trouble, if I rely on the units, it kind of bails me out, so to speak. So what I mean by that, watch this. So we already said that each cross section has an area of 3 square meters. So let's say meters squared, it's over 1. And our function P of H is measured in millions of cells. We'll say M for millions of cells per cubic meter. Now, if I was to multiply those two together, I'm going to get a new function that is millions of cells just per meter. And watch what happens. If I want to integrate that new function that I just created by multiplying these two together, I'm going to get an answer that's just millions of cells, which is exactly what I want when I'm all done, just millions of cells. So that's essentially what I'm going to do is I'm going to say, okay, 3 multiplied by P of H is basically going to tell me how many planktons are in this cross section. Now, within this vertical column, we'll say there's an infinite number of really thin cross sections. And basically, I want to figure out how many cells are in each one of those cross sections and then add them all together. How many are in this cross section, plus how many are in this one, plus this one, plus this one, plus this one, plus every other one that's in there. And to add those together, we're going to integrate them from 0 to 30. And that's with respect to H. And here's the beautiful thing. Now we can just plug this straight into our calculator. We're going to get about 16, and I'm going nearest million here, so 1675 million plankton cells. And again, it was all about, if you're struggling getting to this part where you think, okay, how would I know that I was supposed to multiply the 3 and the P of H together? Just analyze your units. Analyzing your units is going to help you get there. All right, we're moving on to part C. It says there's a function u such that we guarantee that f is smaller than u at all for all h is greater than 30. And the integral of u from 30 to infinity is going to be 105. So here's what you already know right now. You're already thinking, if I was to integrate f of h from 30 to infinity, the answer is going to be less than 105 for sure, guaranteed. Now, that column of water that we just described in part B, instead of being 30 meters deep, it's now K meters deep. And of course, K is going to be greater than 30. So it might be 40, 50, 65 meters deep. We're not sure. Write an expression involving one or more integrals that gives the number of plankton cells in millions in the entire column. So we've kind of already did that 0 to 30 column. And then we're just going to add on to that how many cells there are between 30 down to K. All right. And then we're going to try to explain why that number, and we don't have to come up with that number. We're just going to set up a couple of integrals, but explain why the answer has to be less than 2 million. And that's going to be nice. As BC students, you're kind of familiar with like the comparison tests and things like that. It's going to kind of come out of that mold. So here's what I'm looking to attack or set this bear up. First, we want to figure out, okay, how many planktons were there during the first 30 meters, and we're just basically taking the answer that we'd already set up. So, and I pulled the 3 out, which I could have done in part B. It's totally optional. Plus, how many planktons do we have between 30 meters and K meters deep? And this is going to be 3 times that f of h function that we don't know. We weren't explicitly given. And the good news is we don't have to compute this because, well, we don't know who f is. But they do want us to come up with kind of like this upper bound, so to speak, and try to prove why it has to be less than 2,000 million plankton cells. And here's the analysis that goes into that. So what we know already is that if I integrate, let's say from 30 to K, 3 times f of h, this integral right here is guaranteed to be smaller than who? 3 times the integral of u. Okay, because, and that makes perfect sense. If we already know that f smaller than u, and then we multiply both of them by 3, then that inequality is still going to stay the same way. And what you also know is this one's going to be less than the integral from 30 to infinity of u of h dh. Now, the integral of u of h from 30 to infinity, I think, was 105. And when I multiply that 105 by 3, I get 315. So if you follow the chain of events here, this integral's got to be less than this one, which is guaranteed to be less than 315. So let's attach a safe upper bound there. We've got, going back to our original setup, we'll come down here. The first integral there was what we found in part B was going to be, I think that was what, 1675 plus something we know is going to be smaller than 315. Adding those two bears together makes 1990 million cells. And that number is certainly less than 2,000 million cells. And so that's how we're going to prove that this answer is guaranteed to be smaller than 200 or 2,000 million cells. And that's just, we're creating a nice safe upper bound. Oh, baby, we are almost there. There's a little light at the end of the tunnel here. And just when you were expecting D to be a bigger bear than all the others, this is a teddy bear, just a real innocent one. It was almost like they just kind of ran out of questions. I don't know. But here's what we're looking at. What do we got here? So now there's a boat moving on the surface. We've got this parametric function. You see this parametric function right here? So we've got the rate at which the horizontal position is changing, the rate at which the vertical position is changing, and we are looking for the total distance traveled. And this is just a good old formula we want to make sure we got in our toolbox. So parametrically speaking, the total distance traveled is going to be the integral from, we'll say in this case, from t equals 0 to t equals 1. We have this big radical. It's going to be the x prime function squared plus the y prime function squared. So x prime is like your horizontal velocity, y prime is your vertical velocity. Okay, we're going to evaluate that on our calculator. So we'd have to put this function in our calculator. This function, we're going to make sure we're in radian mode for sure. Bada bing, bada boom. We're going to get 757.459. That's going to be measured in meters because we're describing total distance. And part D is a piece of cake. So, hey, if you like this video, you thought it was helpful, please subscribe and hit like. Add some comments in there. Tell me which parts were still the most confusing, because I'd like to try to redo this and offer a new and improved version down the road, and appreciate all of your feedback. Have a great night. Talk to you guys later.